Distinguished guests, ladies and gentlemen, I would like to echo my thanks, in addition to those from Richard Waring and Joe Landsberg, to the Marcus Wallenberg Foundation for this prestigious award. I would like to talk about how the 3PG model can be used from a plot scale, where it was originally developed, to be applied across stands to landscapes, and ultimately, globally, as a model of forest growth to help us understand the carbon allocation of forests today. Before I go into that, I would like to firstly recognise my co-award winners. Both Richard Waring and Joe Landsberg have been enormous mentors to me. And when I look up the definition mentor in the Oxford Dictionary, you could replace a trusted counsellor or guide with Richard Waring and Joe Landsberg. They have both been very generous over their careers with time and knowledge with me, and have ended up being strong collaborators for the research that I've undertaken since meeting them in the late 1990s. My many thanks to both of them. Joe has given a very detailed breakdown of the 3PG model and why it was so revolutionary at the time as a way of simplifying the concepts and underlying models that we knew at the time to go and build a comprehensive model that could be applied easily over space and time. Joe's acknowledged the important work of Peter Sands, who took the model and then put it into an easy-to-use Excel format. At the same time, we also started to apply the model and develop the code so that it could be run over large areas, working within a geographic information system, allowing us to go and apply the model across large areas, making landscape-level predictions, which are very useful for forest managers. More recently, we've seen a number of other model formulations of 3PG in programs such as R. There are many schematic diagrams that describe how 3PG work. Joe's touched on many of them. When you think about the input variables, though, that 3PG requires, there are a number which can be brought in as spatial variables rather than information from a plot. In 1997, we were just starting to see the development of spatial layers, spatially derived surfaces of attributes like climate, rainfall, temperature, solar radiation. And these spatial layers became critical to applying 3PG over a landscape. At the same time, we started to have very wide availability of terrain models, which provided information about slope and aspect. These are key drivers of the water in the landscape. And so these layers were also starting to be developed from satellite and topographic maps in the late 1990s. As a result, we started to see a shift from polygon-based inventories in forestry to more raster-based understandings. The idea that we would have raster layers or grids of climate that could come in at regular intervals. We could integrate that with information from satellites that were also growing at the time and link them together through long-term plots, such as permanent sample plots. This idea of a spatially explicit inventory was what we started to see coming up in the 1990s and 2000s. And 3PG was right in there as a model that allowed you to hang all these different spatial layers together. And of course, just at that time, we had a revolution in the availability of satellite imagery. Until then, we were fairly limited in the spatial images that we had from space. But in the late 1990s into the 2000s, we had an explosion in different remote sensing satellites that we could use. And I'll talk about how these can be integrated in 3PG throughout this talk. This immediate idea of linking in spatial layers was something that happened almost at the same time as we were developing the 3PG model. I remember working with Dick and Joe as they were preparing the Forest Ecology and Management manuscript, and thinking and discussing with Dick and Joe that there were many ways that remote sensing data could enter the model. And we started working immediately on applying the model in plantations in Australia for Pinus radiata. And here was one of the first simulations we ever did from that integration of 3PG with satellite imagery. We still have the incoming climate, but instead of allowing the leaf area to grow within the model, we use satellite estimates of leaf area index, which allowed us to produce patterns of forest growth at very fine spatial scale, much more than the polygons that we were originally used to that you can see in the top two figures. Now we're able to derive 3PG predictions of growth at a very fine spatial scale, 30 meters by 30 meters, giving us all the richness that the landscape has in terms of driving that forest growth. While we were doing this at the 30-meter scale, we were also looking at how to apply 3PG more regionally. Joe, based at CSIRO, and myself at the time started working with the Australian Greenhouse Office. And 3PG was used by the Greenhouse Office to go away and build productivity strata, but allowed them to go away and understand where productivity classes or gradients were occurring across the country at a very fine scale. This then led the development of strata where plots and additional analysis were put in to produce an Australian-wide carbon balance inventory. Likewise, in New Zealand, the 3PG model was quickly picked up by Landcare, again to stratify the productivity of the forests to allow new plots to be put in to represent that variation. 3PG was also being picked up within CSIRO, where it had initially been developed, and we started to see 3PG being applied at a forest management area. Here we can see the predictions that were undertaken in 2000 and 2001 for the Bago State Forest, which is near Tumbarumba in New South Wales. This was really the first time the 3PG model was being applied at a forest management unit to go and predict variables important for foresters like volume. This interest in 3PG was then growing. People were starting to realize that it could be applied at a plot scale, but also over large areas, and people were starting to integrate these GIS spatial layers. One of the first industrial companies to pick up 3PG was Aracruz Cellulose, based in Brazil. This work was pioneered by the work of Aro Amelia, who's now based at CSIRO, who went away and made predictions of short-term rotation growth of eucalypts within their estates in Brazil, as well as developing software tools to allow the plantation managers to predict what the future forest growth would be for the company. The real innovation here was not only applying it over large areas, but tuning 3PG to work in these very short rotations, in this case making predictions at 7 years for the eucalypt species. Applying 3PG then became more common to apply it over large areas. And this is where the work of Richard Waring, who then was back at Oregon State University, and myself about applying the 3PG model to larger areas of North America. We originally started in Oregon, which is where there was a lot of significant forest growth information and where we had a lot of other collaborators working at Oregon State University. We quickly found that 3PG was able to be calibrated for these conifer-based species in the United States, lodgepole pine, ponderosa pine, Douglas fir, and spruce, allowing us to go and make predictions for these conifer species across the region. We found that the 3PG model was again very accurate predicting key forestry attributes, in this case, the periodic annual increment of the tree growth. Excitingly, we also began to realize that we could model not only the growth, but the mechanisms of growth. As Joe described in his model breakdown, a key part of the 3PG was to build a soil-water balance model that linked to the dynamics of the canopy. Dick himself had done many years of work looking at soil-water balances in Oregon, so it allowed us to go away and compare the 3PG predictions of soil-water balance to measurements taken in the field. And here we can see a drier site versus a much wetter site as part of the Oregon transect, and 3PG is able to model the water and how that water is drawn down in the soil through the summer periods and then replenished again in winter. The rate at which that happens in the different soil types with the different vegetation types was able to be accurately reflected by the predictions of 3PG. This idea of using these modifiers then really interested Dick and myself, and we started applying the model more broadly throughout Western North America. And we started using not only the modifiers such as drought, but also the other modifiers that 3PG produced, for example, vapor pressure, temperature, and frost damage. At the time, climate envelope models for looking at species responses were very popular. 3PG uses those same ideas of climate variability and where a species fits within its niche, but by linking 3PG to radiation estimates and leaf area index, these modifiers are able to be scaled depending on the solar radiation absorbed at the time by the vegetation. This is an important distinction compared to traditional climate-based models which just use temperature and rainfall. As a result, we were able to make broad-scale predictions across all of Western North America for all of these different modifiers, for example, drought, temperature, vapor pressure, and frost. And we were able to track how different species within the Pacific Northwest responded to these different modifiers. So here you can see on the x-axis the seasons of the year, and on the y-axis the impact of the modifiers, where 1 indicates there's not much impact, 0 indicating there's very significant impact leading to shutdown and growth. Different species, for example, Sitka spruce, lodgepole pine, western hemlock, and western larch, respond differently to these modifiers. So as a result, we're able to go away and plot how these species are responding in their environment over long-term periods of time. In this case, for 30 years from 1976 to 2006. Where it's red, we can see that the species is comfortable within its given range. The climate in each individual year matches the long-term climate that species would expect. As we move into the greens, the yellows, the greens, and the blues, we start to see where the species becomes more stressed. In other words, the climate in some individual years is not well suited to the long-term climate of that species. That allows us to go away and work out where in the landscape the species is stressed. And Dick and I have done much work in the last decade, funded principally by NASA, looking at where we have these stress in species all across the Pacific Northwest. And by combining those for different species that we modeled, over 20, we're able then to go away and see where do we have more stress in our species, which is actually shown in the x-axis, and then using satellite data to go and look for examples of disturbances, for example, beetle, infestation, fire, drought, and then comparing that to where 3PG sees that stress occur. What we find is where 3PG indicates the species is under stress correlates very well to where we see an above average increase in insect, disease, fire, and drought. All of those 4 variables then being observed by remote sensing. This work is still being actively done. In British Columbia, we started then to look at where should we be replanting seedlings following harvesting. As we know, we plant trees after harvesting as part of sustainable forest management, but the question now is becoming what is the appropriate species and seed source we should use to ensure that those seedlings grow well in a changing climate. In this thesis work by Amanda Mathis, she took this concept and she looked at where areas are stressed for a particular species, and then where the seedlings are being planted. And then finding a mismatch between the species that we're planting in areas that are likely to be more stressed, providing insights into where we should be changing the species mix across the landscape. Comparing 3PG to satellite-based imagery still today is an active area of research. Because satellites are able to observe these key variables that 3PG is able to predict, we can link those observations together. Here you can see on the left-hand side a prediction of the leaf area index over all of the Pacific Northwest of North America from 3PG. In the middle, we can see satellite observed leaf area index. So the 3PG estimate is what the landscape could produce given long-term climate and information. And on the right-hand side, it's what it actually is as observed from space. Now, as we know, there are a number of different input variables that go into 3PG. Climate, terrain, slope, and radiation are easy variables for us to go and obtain. Information on soil fertility and available soil water holding capacity are more challenging because our soil maps, even today, are not that spatially accurate. So in some work that Dick and I undertook in 2010 and 11 was to go away and try to link these two ideas together to use the leaf area estimates from space as the benchmark, and then varying the predictions of leaf area from 3PG based on different soil inputs. With the logic being, if we had to increase or decrease the prediction from 3PG to match the satellite observation, we could do so by changing the soil attributes, which allowed us then to go away and make maps of the optimum soil attributes across the landscape. And as a result, we produced for the first time fine-scale estimates of soil water holding capacity and fertility across the entire Pacific Northwest. And these ended up comparing well to the traditional soil-based polygon maps that were freely available. A lot of the work that has been done has been linking the 3PG growth model to estimates of leaf area, because they've been readily available from satellite-based imagery. But today, in 2021, we have a wide variety of satellite imagery that we can plug into the model. And how we do that is still an active area of operational research today. Landsat information, which has been available in space since 1972, is driving our understanding of land cover, so we're able to bring in attributes like harvesting and management. MODIS provides leaf area index. We now have calibrated fine-scale long-term estimates of land surface temperature, which are resulting in evapotranspiration layers now being produced from satellite imagery. These can also be readily plugged into the 3PG model to see the water dynamics. We're starting to see more hyperspectral satellite-based imagery available, which is allowing us to directly predict attributes like canopy nitrogen, as well as light use efficiency, which can plug into the 3PG model to allow us to scale the growth depending on the productivity. And lastly, light detection and ranging, the use of lasers from aircraft and space, is giving us extraordinary information from a remote sensing point of view about biomass. So we're able then to go away and better calibrate the model in terms of those relationships between stem biomass, branch biomass, and foliage biomass, allowing LiDAR to be used to help build better allometric relationships. Like Joe, I want to highlight the fact that the success of 3PG model is due in no small part by the fact that it was freely available to use and modify when it was developed. Today, we're seeing a huge push for open source models and data to ensure reproducible science. The 3PG model in many ways was ahead of its time because that was 20 years ago when the decision was made to make the model publicly available. This resulted in very fast uptake and also ensured that people could modify the model as they wished for their own particular applications. If people wanted to improve the soil-water balance model, they could do so. If they wished to parameterize it for different species, they could do so. And then if they wished to parameterize it for mixed species, they could do that as well. As a result, the model flourished because it was freely available and available for people to modify it as they wish, without any contract or payment to make that happen. As a result, after 20 years, we now see it being the most commonly applied forest growth model used today. And whereas we started with that really important paper, the landmark paper of 3PG in 1997, 20 years later, we now have review papers about 3PG to help users continue to do it. And as recently as this year, we have full calibration parameters for a variety of species in Europe, as well as papers now reviewing the model and its application over that time. 3PG's success can be attributed to a large number of factors. Clearly, the openness and collaborative nature of Joe and Richard to see the model be promoted and used widely, the ability of the model to be plugged into geospatial information systems, allowing us to apply the landscape in management contexts, has attracted many people to its use. CSIRO continued to support its development, and of course many other organisations funded research projects to see the model flourish. So many collaborators, for all three of us, have been passionate about the model and to see it run. Too many to list, but they are of course from all over the globe, initially from Australia, United States, and now Canada, Europe, and globally, frequently use the model for a variety of forest management and forest research-based activities today. Again, many thanks for this prestigious award, and thank you very much.